In this video, we're going to be doing another optimization problem involving the optimization of resources. So take a moment and read the example very carefully. As always, the first thing that we want to do is determine what it is we are optimizing. And it says right here, if the company wishes to produce 1,600 snowboards per day at a minimum cost, how many workers and how many robots should it use? So we want to minimize cost. So our objective function is a cost function, is going to be some cost function. So what information do we have about costs? Well, if we go up to the, I believe it is the third line, it says that the daily operating costs amount to $67 per worker and $44 per robot. So we can translate that into a cost function, $67 times the number of workers, which we will let be N, and $44 per robot, which we will use the variable R. So there is a cost function, and that is what we wish to minimize the cost. So that is step one. Step two then is we need a constraint because we clearly have two independent variables in our objective function. So we need a constraint that is going to relate to N and R. Constraint must relate N and R. And so we have that right up here. Q is equal to 70n to the 0.3 power times r to the 0.7 power. So our constraint is Q equals 70n to the 0.3 and r to the 0.7. Now, in order to use this constraint, we should only have the variables n and r. We have the variable q here. So we have to get rid of the q. And that's where we read a little bit more. Well, what does q represent? Well, q is the number of snowboards that can be manufactured by N workers in our robots. And if the company wishes to produce 1,600 snowboards, so therefore Q is going to be equal to 1,600. So we can just substitute that in and say that 1,600 is equal to 70n to the 0.3 r to the 0.7. And so this is our constraint. The only other thing we want to do with the constraint is solve it for one of the variables. And that's the fun part here. A little bit of algebra. First thing that we need to do is divide 1,600 by 70, and that becomes 22.86 is equal to n to the 0.3 r to the 0.7. And I decided arbitrarily to solve it for r. You could solve it for n, it doesn't make any difference. So to do that, I'm going to divide both sides by n to the 0.3, and that would be equal to r to the 0.7. And then to solve for r, we want to raise both sides to the reciprocal power of 0.7. So the reciprocal of 0.7 would be 1 over 0.7. And that gets a little ugly to look at. 1 divided by 0.7. Remember, 0.7 is 7/10. So 1 divided by 7/10 is 10/7. So what I'm going to do at this point in time is change the decimals to fractions. I like to work with fractions better. So 0.3 is 3/10. So what I'm going to have here is I'm going to have 22.86 divided by n to the 3/10 is equal to r to the 7/10, And we're going to raise both sides to the reciprocal power, which is 10/7, as I demonstrated over here. What we end up with then is I'm going to put the r on the left-hand side. R is equal, whoops, didn't put my 10/7 there, is equal to 22.86 over n to the 3/10, all raised to the 10/7 power. Now, we could do some other things to simplify that, but for now, I'm just going to leave it as it is. So this is our constraint solved for r. Constraint solved for r. So that's step 2 complete. Step 2 is complete, which is to find your constraint, solve it for one of the variables. Step 3 now is to substitute the constraint into the objective function. So once again, my objective function is 67n plus 44r. And so I'm going to substitute in r, which was 22.86 over n to the 3/10, all raised to the 10/7 power. Okay, so what do we want to do now? So we want to actually, I'm going to take what's inside the parentheses here, and I'm going to bring up the end of the 3/10 and bring it upstairs. So I have 22.86 times n to the negative 3/10, all raised to the 10/7 power. And then if we raise everything in the parentheses to the 10/7 power, you can do that in Desmos, of course. You raise 22.86 to the 10/7 power, you should end up with 87.4, and then n to the negative 3/10 raised to the 10/7 power. You're raising a power to a power. The 10s cancel out. You end up with n to the negative 3/7. And now multiplying 87.4 times 44, we end up with 67n plus, I believe that comes to 3,845.83 n to the negative 3/7. Okay, so that is step 3. Step 3 is complete. That is where we substitute the constraint into the objective function and get it in a form where we can now take the derivative. So step 4 is actually optimizing. So we want to find the derivative, C prime. Well, the derivative of 67n is 67. And the derivative of the second term is we have to bring the negative 3/7 down and multiply it by all of this. And when you do that, we're going to end up with a negative, and in decimal form, 1648.21. And then negative 3/7 minus 7/7 would be n to the negative 10/7. So there's my derivative. So as with any optimization problem, the next step, once you have the derivative, is to set it equal to 0 and solve. So first step there is going to be to take this and put it over on the other side of the equal sign so it's not negative. So we'll have 1648.21 n to the negative 10/7 is equal to 67. Divide 67 by this stuff over here. We have n to the negative 10/7 is 67 divided by 1648.21. And that ends up being 0.04. So n to the negative 10/7 is equal to 0.04065. And now to solve for n, we will once again raise both sides to the reciprocal power, negative 7/10 power. And so we end up with n is equal to 9.411, which would be approximately 9 workers. Now again, in Moore, I'm not sure how it's doing the rounding, but if you have 9.4 workers, you can't have a fraction of a worker, so we would round that to the nearest integer. That would make sense. So I would say 9 workers. All right, well, now to find the number of robots, we go back to our constraint. And our constraint was 22.86. Let's see, let me write it in the same form I have here. Where was my constraint? 22.86 over n to the 3/10 over n to the 3/10, and then that was all raised to the 10/7 power. Okay, well, plug in 9, so you'll have 22.86 over 9 to the 3/10 power, all raised to the 10/7. And so when you go through, do that in Desmos, R will be approximately, 33.43, which is approximately 33 robots. And again, take a look to see how Moore wants you to do the actual rounding of that. So we have now found the number of robots and the number of workers that we need to maximize or to minimize our cost. And I believe that is what we needed to answer. Let's go back to the problem. It says if the company wishes to produce 1,600 snowboards, which we did, at a minimum cost, how many workers and how many robots should it use? And round your answers to the nearest integer. All right, so we are done.